Hi, this is Mrs. Vrobel. This is Chapter 7, Ionic Compounds and Metals, Part 3. So in this video, we're going to look about the strength of ionic bonds based on the physical properties of ionic compounds. Then we're going to describe what is a metallic bond and how it relates to the electron C model. And then we're going to describe the properties of metals based on the electron C model. And then lastly, we're going to look at what is an alloy and how do we categorize them. Okay, so when we're looking at ionic compounds, we know that there's a ratio of these ions, and the electrons are always transferred. They're never shared. They typically go from the metal atom to the non-metal atom. Now, when they get together and they form an ionic bond, there's a repeating pattern of the cation with the anion, and it essentially forms a crystal. So here is an example of a sodium chloride crystal. So notice that the green spheres represent the chloride ion, which is bigger. Remember, it gained an electron, okay? So there's a little more repulsion and it takes up more space. And the sodium ion lost an electron, okay? It gave it to the chlorine atom, and as a result, it got smaller. Okay, so there's a strong attraction between the positive and negative ions. It's sort of like when you have the opposite poles of a magnet come together, and we have a nice crystal lattice. So crystal lattice is sort of a geometric arrangement of the particles. And you may notice when you take geology that this actually helps to form certain structures within minerals. Now, we need to look at melting point, boiling point, and hardness. If you notice with these ionic compounds, the melting point is gradually getting higher. Look at magnesium oxide. It's 2,852 degrees Celsius. That's pretty high. So for a solid, it's a very high melting point. If you look at boiling point, so boiling point means it's in its liquid form. It takes a lot of energy to get to 3,600 Celsius for its boiling point. So I would argue that these last two data points show that magnesium oxide has a very strong attraction between the cation and the anion. Okay, so please remember, if you're talking about a solid crystal, the ions, they essentially are stuck in place. And because of that, we can't see the electrons moving around as much. So as a result of it, in the solid form, you're not going to get a whole lot of electricity being conducted. However, once you move to a liquid state, something completely different happens. So the electrons now have the ability to move. And as a result of it, we get electricity conducting. And I'll make sure I show some examples in class for you. So please note, when we're talking about a water solution or an aqueous solution, you're going to get conduction of an electricity, and we call that an electrolyte. Okay, so why do I show you this picture? Well, this is to help us understand why, if you were to hit a piece of salt crystal, why it breaks. So we have regular repeating pattern of cations and anions. When you hit a solid crystal that's ionic, you're disrupting the crystal structure. So as a result of it, if you have two positively charged ions right next to each other, they're going to repel each other, and as a result, they're going to push away from each other. So this forces the crystal apart. That's why these compounds tend to be brittle. So let's talk about what we call the electron C model. So this is a little bit different from ionic compounds. What happens is when you have metals with each other, you essentially have different energy levels that are overlapping with each other. Now, as a result of this, you have overcrowding, and you don't want that. But with an electron C model, a lot of scientists have seen this in metals, that the electrons that are in the outer shell or outer orbit of an atom, they actually flow from one atom to another. And we call this delocalized. So they're free to go from atom to atom. They're not stuck at one place. And this is all a combination of metal cations. I'll show you a picture of that. So here we have a lattice of metal cations, and notice that they space themselves out enough so that they're not too close to each other. They're not necessarily repulsed by each other, but the electrons can kind of flow in between them, and they go from atom to atom to atom. So they don't stay with just one atom, and we call this a sea of electrons. Now, the interesting thing with metals is we have more extreme situations here. Here we have just cations that are in a crystal or lattice state, and depending on the attraction that they have with each other, the energies are going to be different. Notice that when we're looking at lithium metal, and please remember, lithium has just one valence electron. It has a very low melting point. Its boiling point is relatively high, but notice when you look at copper, its boiling point is significantly higher. So the attraction of the cations with the electrons is much stronger. So as a result of it, you have to put more energy into it. And the same thing can be said of the melting point. Copper has a higher melting point because the cations are attracted to their electrons and hold together in the solid state. Okay, this is a little bit different scenario than ionic compounds. You may notice that you can bend or you can hit metal and it doesn't break. Well, the reason why is because it has that sea of electrons that help it to be more bendable. And as a result of it, you may notice that metals, they can be pulled into wires. So if you make jewelry, you may notice that when you have a thick piece of metal, you can actually pull it into a wire. It takes some effort, but once you do, you're able to get it into a wire and it doesn't break. And that's because that sea of electrons is holding the solid metal together. Okay, so the electrons move around the cations, and as a result of it, they are good conductors of metal heat. That's why we use metal pots and pans on our stove, because they are able to transfer the heat more readily. And if you have more electrons available, you'll probably notice that the strength of the metal increases and the hardness of the metal increases. Okay, so one more thing we need to talk about is alloys, and you've probably heard the term alloys before. It's essentially two or more types of elements that have metallic properties. And alloys help to create a different type of metal. And I'll give you some examples here. We have substitutional and interstitial, and you're going to make one of these in class. Substitutional is this bottom left-hand picture here. So with substitutional, notice this blue atom is the same size as this red atom. So when you make a substitutional alloy, you want to make sure that the atom sizes are the same. And like I said, we're going to do a lab where you make a substitutional alloy. Interstitial is a little bit different. The element that you want to combine with the first element has to be smaller. And when it's small enough, it can actually fit between two larger atoms. Sometimes it gives it more rigidity or more strength. Okay, so in summary, ions are organized into repeating patterns, and we call this a crystal lattice. And you might notice that the ionic properties tell us what actually is the strength of the bonds between the cation and the anion. Please remember that compounds need water typically to conduct electricity, because the electrons don't readily flow in the solid state. For metallic bonds, we're looking at cations, and in this regular pattern of cations is a sea of electrons that freely move from atom to atom. So in the C model, please remember that the electrons don't stay with one particular atom. And then lastly, with alloys, you can have two or more metals that have metallic properties. And when you add that second metallic element, it typically changes the properties of that metal.